Hello and welcome to part 2 of our do-it-yourself programming language. In this video we're going to look at handling more sophisticated input by using a finite state machine to parse the input into tokens. Tokens are tangible nuggets of information with which we can pass on to the Shunting Yard algorithm to then go and do useful things with, such as solving or compiling. Now, I appreciate this video is quite long, but there are a number of fundamentals to get through to make sure that the parser is robust and versatile enough to be useful in subsequent episodes. So let's get started. In the previous video I showed the Shunting Yard algorithm, but it had some very bold assumptions to make it easy to demonstrate the algorithm, but it actually made it very impractical to use in the real world. For example, we had an input expression that looked like this. 1 plus 2 times 4 subtract 3. Input was provided to the algorithm in the form of a string, and it was a very carefully curated string because each digit or each character of that string had something useful about it. And we could iterate through the string from the beginning to the end. Because everything that we could process was represented by a single character, it became quite an easy thing to parse. We could quite easily ask the question, is this a numeric digit? Well, yes it is. No it's not. Yes it is. No it's not. Yes it is. No it's not. Yes it is. If it's not a numeric digit, then it's going to have to be an operator. However, in the real world, we want to work with more interesting things, so we may have something along the lines of 1.0013 plus 2.61 times 4 on its own, take pi. Hopefully, it's clear to see that our single numeric token now is multiple characters, and it has things in it that are not strictly digits. And because we're computing nerds, we may not just want to work with numbers, we might want to work with other things, so 0b011 plus 0x2fa times 4 take pi. Okay, you'd have to be relatively insane to actually work with something like that, but it's nice to have that flexibility. But that flexibility comes at a cost. We've now got 4 different numeric standards of representing a numeric value in our expression. It could also be the case that in the future our operators become more sophisticated. For example, we might have more than one character to represent an operator. And we may also find ourselves with the dreaded unary operator also sneaking in too. One of the advantages of being able to iterate from the left to the right of the string is we could also apply the Shunting Yard algorithm at each stage and sort it all out. And with that, we have defined the premise of this video. I want to take a human-readable sludge of all sorts of mess and turn it into something structured and ordered that our computer can understand. I also want to keep my mind open to the idea that as we progress through the series, we're going to want our DIY programming language to grow in terms of sophistication. So there might be other things needed alongside numeric values and operators. To handle this, I'm going to use a finite state machine. And it's certainly not the first time on OLC that we've used finite state machines. But a little refresher never hurt anybody. It's essentially a posh way of describing a form of computation. At any one time, we can exist in a state. States have inputs that can trigger a move to a different state, which in turn can move to another different state. It could potentially move back to the state we've just come from. Let's start with a very simple expression, this string 100 plus 35. It contains multiple digit numeric literals. Us humans are very good at observing that this is a token, this is a token, and this is a token. So even though the string contains 6 digits, there's really only 3 relevant bits of information. Our computer, however, can only see 1 digit of the string at a time, but it can see them in order. So I've developed a small state machine that looks at the first digit and then decides how to proceed. Completed tokens are then built up as we progress through the state machine's loops. My first state I'm going to call new token. It works a bit like a reset state. Any currently accumulating token string is reset. My state machine is always going to be looking at the front of the string, but can consume digits. So right now it can see the digit 1, but it's not consumed it from the expression. The first digit of a token is invaluable in deciding what that token might be. So in this state, looking at the digit 1, I'm going to ask the question, is it a digit? And if it is a digit, it's likely my token is going to be a numeric literal. So I'm going to append the character to my token string. If I append a digit to my token, then I'm going to consume it from my input string. I'm still in the numeric literal state, but now the front of my string is this 0. So I'm going to ask the question again. Is it a digit? Well, exactly the same thing happens. It is a digit, we consume it, but we remain in the numeric literal state. And then it happens again. The front of the string is 0, so we consume it, add it to our current token, and we remain in the numeric literal state. Now, the front of our string is this plus symbol. This is clearly not a digit. It's not a digit, so I'm not going to consume it just yet, but I am going to finish off my token, classify it as a numeric literal, and go to my complete token state. The complete token state outputs our classified token to some output container, but then immediately moves us right back to our new token state. Recall, this resets our accumulated token. The plus symbol is in our known character set for operators, so we can ask the question, is operator? In much the same way as we have just done with numeric literals, we will accumulate the current token with valid operator characters, and we can keep looping in this state, consuming each time, just as we did with numeric literals, until the character is not an operator character. We've already got a state to handle the completion of tokens and outputting them, and that will automatically take us back to the new token starting point. Hopefully, with this very crude example, you can see we will end up with 3 strings from our output. And not only are they just strings, we know that this is a numeric literal, this is an operator, and this is a numeric literal. We can include this meta information with each token. Now, I have simplified my state machine somewhat to fit it all on one screen like this, but the principle is what we will be expanding upon throughout the rest of this video. But I thought, let's start here and replicate what we did in the previous video. This time we can use multiple digit numbers. This will give us a good base then from which we can start to add the new fancy features. It's also an opportunity to just quickly discuss some housekeeping required as part of this project's development. Even though this is a continuation, I'm starting with a blank file. We're now starting to not look at the individual algorithms in isolation, we're working on the final DIY programming language framework. And as such, I'm going to add in a bunch of standard library things that we use quite a bit of, and I'm going to create the namespace OLC lang. No doubt, once we actually get around to naming the language, that might change. In the Shunting Yard video, we created a struct called symbol. I'm going to change this to simply token. It made sense in the previous video to call them symbols because they had meaning associated with them, but in this video we're looking at just specifically having tokens. We don't really know what the tokens might mean at this stage. I'm going to tidy up this struct a little bit. I'm not going to contain an operator equivalent. We'll see why later. And I'm going to rearrange the ordering of the token. Some of our inline initializers later on are a little more clear. Each token will consist of the type, as it did before, and the text of that token. For the time being, I'm also going to store in the numeric value if applicable to this token. That just makes things very convenient and keeps the code clear when we're working with just values later on. I also want to add to this token structure the ability for it to describe itself as a string. This is useful for debugging, and so for each type case, I will add in the string equivalent. Finally, I'll append the token's value itself. Again, from the Shunting Yard video, we had a structure called S-operator. Well, I'm keeping this just the same, except I'm dropping the Hungarian S at the start. Now, as part of my ongoing efforts to upset the internet, I'm going to throw in an error exception. Ooh, this is a first for one lone code, I think. We don't usually use standard exceptions, we usually just crash out. But that's quite inconvenient for somebody that's writing code and it causes problems. You want it to crash out in a controllable way. But at the same time, I don't want to bog down my code with thousands and thousands of nested anything in order to sort it all out. I believe this is a good use case to use standard exception. At the moment, it's called compile error, and it doesn't do anything particularly fancy other than wrap a string which we can display with our error message. And finally, I'm going to create a class called compiler. I didn't do this previously because we had no requirement for isolation between different rounds of compilation. We still technically don't, but we will do in the future, so it's useful to have this map of operators actually belong to something rather than just floating around in a namespace. And yes, this map of operators has the same purpose as it did in the Shunting Yard video. For the time being, the constructor of the compiler will define a few operators already, and for almost being cancelled for an egregious lack of integrity, let's fix this quick bug right now. Done. Hopefully that has gone some way to sedating the armchair coding guardians of the internet. To my compiler, I'm going to add one more function, parse, which takes a standard string of input, does some magic using a finite state machine to produce a vector of output tokens. If we didn't provide any input by accident, it's a good time to test our compile error exception mechanism. And it is here where we need to implement our finite state machine meaty goodness. Our source file doesn't have an int main, so let's quickly add one of those too, to make sure we can test things quickly and easily. As in the previous video, I'm going to have a string called sExpression. This time you can see I've inflated the digits just to make them a bit more interesting. And then, very fancily, in a try block, I'm going to call the parse function we've just created on this expression. And if there's a problem, I'm going to catch any error that it throws and display that to the user. If there aren't any problems, the parse expression returns a vector of our tokens. I'm going to iterate through those tokens and call the string function upon them to display them. So yes, a little bit of housekeeping to get out of the way there, but now let's crack on with implementing a finite state machine. Now, one of the problems with state machines is that they yield quite repetitive and at times often verbose and rather large code. That's just the price you pay for the power of organization a finite state machine might give you. To keep track of what state I'm in, I'm going to create another enum class inside this function called Tokenizer State. And first time round, I'm just going to add in the states we've already talked about: new token, numeric literal, operator, and complete token. In the interest of expediency and to have parity with the previous video, I'm also going to add in two new states, parenthesis open and parenthesis close. Now here's an important thing about state machines. You need two variables to track the state. The first one is state now, which, as its name suggests, is what is the state I am in now. And then when I need to, and under my control, I can transition to the next state. What this means is that whenever we want to change state, we set state next to whatever target state we desire, and only at one point in our program do we set state now to state next. Changing a finite state machine's state halfway through its implementation can often yield bugs which are very difficult to track down. In fact, it is a violation to do so. The beautiful thing about programming, however, is it is possible to do so, and sometimes it can save your neck. But let's try and do this by the book as much as possible. As we progress through the input provided to this function, we're going to consume characters from it, and we want to keep doing so until there is nothing less to consume. That's when we can leave our state machine. So while there are still characters left in our input, process our state machine's state now state. Only once we have finished processing the current state can we update to the next state. State machines don't have to be included in a while loop like this. Sometimes it's implicit. Perhaps a function is called every frame and that function belongs to a particular state. Perhaps there is some sort of external clock input that causes your state machine to tick over to the next state. How that's defined is up to you. But for our purposes, every character in a string will cause the state machine to think about what it's doing at least once per character. Our first state is basically our reset state, new token. Recall, as I'm iterating through the input expression, we're going to be accumulating tokens as strings individually. I can also start to composite the current token I'm reading in. Our reset state should do exactly that. I'm getting a little red squiggly here, which is telling me something's malformed about my token definition. And indeed it is, because I cut and paste the code from some prototype that I've made prior to making this video. Sometimes little errors like this creep in. I don't need to define type twice. So apologies for that, I'm only human, but it does go to show that these things are a little bit live. When we're in our new token state, we said we were going to do some first digit analysis, or first character analysis, depending on where you're from. Now, we said that the first thing we might want to check for is numeric literals. The eagle-eyed amongst you may have noticed that I've created what's called an iterator here, called character now. And my while loop is contingent on character now not being at the end of the string. Character now being an iterator also has a value at all times, which I can access with the asterisk symbol. However, I don't think visually that's clear enough for me, particularly when the code gets complex later. So I prefer in this instance to use a 0 index of the array operator on the char now iterator. And if we wanted to check for numeric literals, we might do something along the lines of is standard digit char now is 0, that's what I was just talking about. If that's true, then the character supplied at that point in our input is a numeric digit. If it was a valid numeric digit, we can set our current token to be that, and we can tell our state machine to go to the next state, which is going to be tokenizer state numeric literal, and most importantly, we must consume that character. This consumption is performed by incrementing our iterator. Char now 0 now points to the next character in our string. The standard library function isDigit is the correct function to use, but I don't like it, and this is one lone coder, and I often have a tendency to go off on a different path, rightly or wrongly. One of the problems, or indeed one of its powerful features, is that it can detect locale, and it's reasonably language and character encoding independent, and it has lots of interesting features that make it very safe to use. All of those interesting features actually also make it quite slow to use. We did some science on this on the Discord server, and found out that it is quite quick, but it's not that quick. Now, given a source file might contain many different characters, I want something really quick to do this assessment. And we're going to need similar functions for assessing different types of tokens. So instead of this being a standard isDigit, it should be something along the lines of, is the current character considered an acceptable member of a set of characters that define numeric literals? And solving that problem is where we start to add some rules for what are the capabilities of our compiler for our custom language. A more visible equivalent might be something along the lines of this. Here we ask the question, does this string of digits contain the character we're looking for? If it does, then it's considered a numeric literal digit, and if it doesn't, it carries on. It's almost functionally equivalent to isDigit. However, now we've got a linear search for every single character. That's still also quite slow. We could also do this, which I know will really upset some people. But because we can exploit the ASCII ordering of these characters, we can do two simple checks to see if the current character is a valid numeric digit. This method might seem quite nice, but then what happens if our set of acceptable digits has other things that we want to get to, and we can't necessarily represent them as a range? For example, as we will see, we do need the decimal point. This could get very messy quite quickly. So I want something that's consistent, easy to construct, and flexes some of my modern C++ muscles. Yes, I am nodding my head. At the top of my namespace here, I'm going to create another namespace called LUT. This is sort of an internal inner workings namespace. It stands for Lookup Table. I'm going to throw memory at this problem to make it go away and have instantaneous lookups. I'm going to start by creating a const expression auto function called makeLut, and it takes in a string view, get that, a string view of acceptable characters. Because it's const expression, I can call it at compile time, nice and easily. So let's have a look at what's going on here. I'm creating something called numeric digits that calls my makeLut function, and to that makeLut function I pass a string of the characters I want to be acceptable for that set. The makeLut function itself really just contains a standard array of booleans. It contains 256 of them. I'm going to assume we're only allowing ASCII characters, and extended ASCII characters to some degree, in our language. Now that's a big problem because it does rule out most foreign language characters, and this is why you should probably stick with the standard library functions provided by the C++ language. However, this makes videos a bit more interesting, and perhaps shows some techniques where we can actually use const expression in a really valid way. I'm going to initialize the array of all 256 booleans to false, and then I'm going to take the ASCII or 8-bit equivalent of the input characters and set that location in the array to true. I'm going to return that array, which gets copied over to our numeric digits. So this allows me to construct a set, and we can see it here with the tooltip, of false, 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 but true where it needs to be. So if I wanted a set of numeric digits and an alternative set of real numeric digits, because they include a decimal point, it's now very easy for me to construct that. And whilst I'm here, I'm also going to create a set of white space digits too. Again, there is a standard is white space. I think it's called standard is space. But you're not going to get much faster than just looking up an array directly with the character value. So getting back to it, I can now simply call the at function of the standard array for the set of digits I'm interested in, passing in the character as the index. And that will return true or false as to whether this character is contained within that set. And it will do so pretty damn quickly. I'll leave this here because this is the code that ends up on the GitHub. Since we just added the ability to detect white space, let's just handle that too as part of our first digit analysis. We look it up in our lookup table. If it is white space, all we're going to do is consume it. We have literally nothing else to do. We don't want to output any tokens. We just want to consume that thing. If it is not white space, then we can start checking to see if it is a numeric literal. Let's add in the case for our numeric literal state to close this loop. Remember that we enter this state having consumed the character, and our current token has already been set with the first digit. So let's check if the new digit at the front is part of our set of real numeric digits. If it is, append the digit to our token, consume the digit, and stay in our numeric literal state. If it's not, then we're done, so set our next state to be our complete token state, construct the token by classifying with what it is, it's a literal numeric, and for convenience, I'm also going to convert the string value to a numeric value. This has introduced a new state now, complete token. Well, recall from the presentation that the complete token state doesn't do very much, it just pushes it into our vector and goes back to the reset state, new token. I'm going to add a set of digits for our operators to be constructed of too. Now our first digit analysis becomes quite a trivial state to implement. If it's not white space, and it's not been a real numeric digit, then let's check to see if it's an operator digit. If it is, we'll move to our state operator. Operators are a little trickier now. Originally, our operators were single-digit things, but this does limit the number of operator symbols available to us that might mean something useful to the programmer. It's quite often, for example, in C++ to see x++. This is an operator, and it means increment the value of x. This can lead to rather confusing things. For example, this is potentially valid, because x++ would go away and add value 1 to x, and then we would want to go and add 2 to that value. We've smushed up our operators. We know that a ++ is a valid operator, and this regular plus symbol is also a different operator. So we have to start making some assumptions and rules of our own to resolve this ambiguity. And I'm going to work on the assumption that my operator determination algorithm is greedy. It looks for the longest valid operator it can first. So assuming we've got a list of stored operators somewhere, we want to keep reading operator digits until we can match it with something. When we read the third one, if that makes it invalid, then at least we knew that this one was valid, so we can write that one off. And then we can start our process again. This means our operator state in the state machine has a little bit of work to do before it can decide whether to move to the complete token state or remain in the operator state. Note that when we performed our first digit analysis, we did not consume the character for an operator. When we enter our operator state, I'm going to check that it is indeed a valid operator digit. We'll come back to what happens if it's not later. One of the tricky things about thinking with state machines is you have to think in parallel slightly about what's going on. We know in the background all of our states are accumulating current token, which is the text form of the current token we are deducing. So let's check if the current token plus the current front of our input is a valid operator. Is it contained within our map of operators? Note that we've not actually changed the current token yet. We're just doing, well, kind of a forward-thinking check. If this resolves to true, then keep going. We've got a larger operator, so append the current character to our current token and consume it. If this was false, then the current character was a valid operator digit, but combined with the current token is not a known operator. Therefore, we have reached the largest size operator that is known to us via current token. So we'll just confirm that the current token is indeed a valid operator. We know that the next character added to that is not a valid operator, but we're being greedy, so we'll bank that one now by moving to our complete token state. Now, all the time, the digit is a valid operator digit. We know that the next character does not yield a valid operator, and we know that currently our current token is not valid either. So we're in a rather strange state where we might have an operator coming up, but right now we can't determine it. So we'll just keep on going. We'll accumulate that character into our current token string and consume it. We're growing some operator which is currently not valid, but it might be later. It might be that it's 4 or 5 digits long, this operator, and we've only got around to testing the first 2 or 3. If we're still in the operator state and the digit was invalid, then confirm that the current token is legitimate. If it is, go back to our complete token state, or throw an error because we've got a valid set of operator digits, but it's not recognized as being in our map of operators. We've come across an unrecognized operator. So yes, the operator tokenizer state is a little bit more complicated because of this greedy nature to consume the largest operator it can do first. Note that now we've got several pathways going through to complete token, we've not had to change it at all. This is one of the nice things about a state machine. That functionality is already there for us. We go back to our state machine definition, you'll see there's 2 more, parenthesis open and parenthesis close. This was to bring parity with the previous video. Let's go away and implement those states now, but these are trivial. In our first digit analysis of our new token state, I'm going to have 2 explicit checks for an open parenthesis and close parenthesis. I don't consume the character, but I just move to that state. Arguably, you don't even need an explicit state to handle these, but I'm choosing to because I do have some behavior which is unique to being in these states, and I shall demonstrate that now. I'm going to grow the current token, even though it's obviously an open parenthesis, and I'm going to consume it. This is just to keep the pattern consistent across all the states. And then immediately I'm going to move to complete token, having classified this token as a parenthesis open. At this point, I'm going to introduce a new variable. It's a quick and dirty hack just to check that I've got a balanced number of parentheses in my application. Every time I open a parenthesis, I'm going to increment this counter, and every time I close the parenthesis, I'm going to decrement this counter. Hopefully, this should be 0 once we've compiled the script. I'll need to create this variable outside of my state machine, and upon exit from the state machine, I can do a quick check. If this value is not 0, then the parentheses are not balanced. We'll see in a future episode how we can add more information to this to actually tell us where it's not balanced. It does seem like we've written quite a lot of code today, but a quick recap before we give this a whirl, because it's important to make sure that we're off to the right start. We've created a very quick way to make sure if a character is part of a valid set of acceptable characters for the thing we're trying to tokenize. We've created a token struct, which understands its own type in its value and has the ability to display itself. We're using exactly the same operator implementation as we did in the Shunting Yard video. I've added an exception type called compile error just to make throwing errors easier and more understandable to the user. And we're encapsulating our functionality inside a class called compiler. At the moment, we just have a map of operators and we've just got the 4 bog standard operators we would normally have. To this compiler class, we've added a function called parse. Parse contains a finite state machine. Right now it just has a small number of states. The state machine is effectively stimulated by each character in the input expression. And for each character, we can determine what state to go to next or remain in the current state depending on the criteria of exit for that state. As we move around the state machine creates tokens. It does that by looking at the first digit of a blank token and then moving on from there. If the first digit is a number, then it will go and try and interpret the largest number of digits it can that remain a valid number. The same applies for operators, providing the operators exist as defined in our map of operators. The states themselves are reasonably simple. The operator state is a little bit more complicated because it has to be a little greedy. That allows us to have multiple digit operators next to each other in the input expression. And finally, we're starting to add in the very basics of syntax checking by putting in tools like the parenthesis balance checker. Our state machine has a completion state which pushes that token to our vector of output tokens, and we return that vector of output tokens to the user who called it in the first place with the expression. If there's a problem, that will now throw an exception, and we can catch that in this try-catch block. Let's take a look. At the top here, we have our input expression, and it has been broken into tokens. The first is 100 plus open parenthesis, then a numeric literal 20 times 40, close parenthesis. Then we've got an operator. It could be unary, it could be binary, we don't know yet. All we have done is tokenize. These tokens have some definition, but there's no meaning applied to them yet. In fact, because we define sets of real numbers, we should be able to put in more interesting numbers for them to try and parse. This works because the decimal point character was part of our set of characters allowed in real numbers. We have a problem, however. I can put in 2 decimal points in a number. That's clearly not valid. We'll need to handle that. I can also see what happens if I put in invalid symbols in a number. Well, it just seems to have crashed. Not very good so far. What we have started to develop here is a very rudimentary form of syntax checking. As I don't really have any description for this language yet, and I'm not entirely sure where I'm going with it, I can't set up a list of hard and fast rules for us to follow. But what I do know is that we're going to need things like symbols. So anything that we don't readily identify as being a literal or an operator or white space or something else that we already know, I'm going to say is a symbol. Well, checking for multiple decimal points is quite easy. I'm going to create a boolean b decimal point found, and in our reset state, set that to false. In our numeric literal state, we want to make sure that only 1 decimal point is allowed. So I'm going to check if the input character is a decimal point. If it is, and my decimal point flag is already set, then this is an error. This means our numeric literal contains 2 decimal points. However, if the character is a decimal point now, and our decimal point flag is false, then just simply set it to true. That's allowed. Let's try this with this dodgy expression. Very nice. Our exception was thrown, and it tells us there was a bad numeric construction. Solving this problem, however, is more complicated, and it requires us to introduce a new type of object into our parser. Our input expressions only know numbers and operators, but that's quite limiting in the real world. Eventually we're going to want variables, function names, and other properties about our input expressions, which are described in a written way. Since we don't know what these might mean, but we know what they are, the best we can call them is a symbol. The parsing stage of our compiler doesn't care about the meaning of things, don't forget. It just cares about what things might be. I've added a set called symbol name digits, which are the valid characters for things such as variable and function names. You can see it's really upper and lowercase letters, the period symbol, underscore, and some numbers. As with most languages, we'll start to need a rule that describes what our symbols can legitimately be called. For example, 1, 2, 3, ABC is invalid because you can't have any symbol beginning with a number. That's one of our rules. ABC 1, 2, 3, however, is completely valid. That's basically a variable name with a number as a suffix. We need this symbol state in our state machine to handle the unknown. Whether we process it or not is a topic for another time, but let's at least handle it. I'm going to add to our state machine the symbol name state. And essentially, we will know whether it's a symbol or not from our first digit analysis, because if it's not anything above it, then it's something unknown. it's potentially a symbol. Since it's unknown, all I can do is consume the character and start a new token, and enter my symbol name state. Just like with the numeric state, we'll keep accumulating symbol name token as long as the character at the front of our input is legitimately a symbol name character. We'll do that until the character isn't part of our symbol name digit set, at which point we'll just complete the token, call it a symbol, and move on. Don't forget we have some rules to enforce, that we can't have numbers preceding symbols. So we'll make that check in our numeric literal state. Here we've been accumulating valid numeric literal characters into a token, but we've found something that isn't a numeric character. It could be an operator, it could be parenthesis, it could be something else. And that's legitimate, but what isn't legitimate is if it's a valid symbol character. We've ended up in a situation like this, which is an invalid token in our environment. Sorry, golfers. Now when we run our program, we can see that there is an invalid number or symbol. In fact, we can start to test these things in isolation. So 1, 2, 3, ABC should be invalid. It is. But ABC123 could be a legitimate variable name. Not a problem. It's just identified as a symbol by the tokenizer. If we put a space in between these, ABC123, we can see it's two tokens. It's a symbol called ABC and a numeric literal. That is fine. ABC123.4, the whole thing is considered a symbol. Again, legitimate. That's fine, because we've allowed periods to be part of our symbol naming rules. ABC plus 123, again, just fine. Having double precision numeric literals is all very well and good, but inside I am an embedded systems nerd. I need binary and hex. To handle these two additional forms of numeric literal, I'm going to add in two more sets of valid digits. One for hexadecimal, as you can see I've got the lowercase a, b, c, d, e, f and the uppercase, and binary digits, 0 and 1. Oh, that's nice. For the time being, my language is typeless. Everything will resolve to a numeric double, and we'll look at that in a future video. But parsing these new numeric literal types in our finite state machine does require some additional states. I'm going to throw in fancy numeric literal, hex numeric literal, and binary numeric literal. We start checking for numeric literals in our first digit analyzer. So far we've assumed that we're always going to be doing a base 10 numeric literal. Well, if the numeric literal is prefixed with 0, that may or may not be the case. We have to make that determination. So if the current character is 0, it could be hexadecimal or binary. If it's not, then it's definitely going to be base 10. I'm going to adopt the C++ style conventions for this, and prefix things with 0x whatever for hex, and 0b whatever for binary. If we're in a non-base 10 state, then I want to go to fancy numeric literal, because the next character determines where we go next. After my numeric literal state, I'm going to add in my fancy numeric literal state, which is where I check the next character. We've consumed the 0 at the start, and now if it is a lowercase x, we're going to move on to hexadecimal, and if it's a lowercase b, we're going to move on to binary. Notice I'm about to add an additional string variable called fancy numeric literal token. I don't want to interfere with the actual token. I want the 0x or the 0b at the start. But when I'm actually turning that into a number, I don't. So this is just a way of keeping the two separate. This is just one of those ancillary things like decimal point found. If the second character wasn't an x or a b, and it wasn't part of the set of real numeric digits, in which case just go back to being a numeric literal, then clearly we've got some weird construction going on, so we'll just throw an error at that point. Let's add in now the case for handling hexadecimal numbers. The case for binary is almost identical. Let's make sure that our first digit is valid hexadecimal. If it is, accumulate these until it isn't. If the character isn't valid hexadecimal, then we want to store it as a token. However, just like with numeric literal, we want to make sure that it isn't also running into being a symbol, because that's not part of our rules. We don't allow that to happen. Create the token in preparation for being pushed to the output stream, and convert the hexadecimal value into a double, just for convenience. We can do that straight away, actually, with the string to long function, and passing in base 16. binary numbers are almost identical in their construction, except this time we're looking for the allowed binary digit set, and rather than base 16, it's base 2. I'm just going to quickly modify our tokens string function to display the value of any literal numerics that get passed in. This will help us to debug these new numeric literal types. Here is an input expression containing now all 4 types of numeric literal our parser will understand. Let's take a look. So there is the input expression at the top. We can see the first one was interpreted as binary, which is 4 and 2, which yes got the value 6. Here we've got the hexadecimal one, which I'm guessing that's the right value. Here we've got one with a decimal point, which was fine, and here we've got one just as an integer. As discussed, at the moment everything resolves to a double. If I malform my hex here by putting in the letter M in the middle of it, hexadecimal literal is malformed. Good, our errors are starting to help us out. What I'm about to do next may seem a bit odd in the context of the video so far. I'm going to add in a few additional features we'll need later on in the series, so this is tying up a few loose ends. I appreciate that right now, adding additional types of token might be beyond the scope of this video, but it's necessary for later videos in this series. Fortunately, they're very simple additions to add to our state machine, so we can really rattle through these. You've seen already parenthesis open and parenthesis close, scope open, scope close, end of statement, separator are all implemented exactly the same way. So I'm not even going to show them. The only 2 left are literal string, which is something defined in quotes, which is quite interesting, and keyword. Our state machine will need several more states to handle these, but again, they're near direct comparisons to parenthesis open and parenthesis close. We'll leave those for the time being. One that does matter, however, is string literal. Let's take a look at that one. We'll check for a string token in our new token state as part of our first digit analysis. Strings in my scripting language are defined as beginning with open double quotes. So if we encounter that as a first digit, then we move into our string literal state. The string literal state consumes all characters into a growing token until it encounters another double quote. When that happens, we classify the current token as a literal string, and eventually it gets pushed to our output tokens. You'll notice that if it is a double quote, either at the start or the end, I'm not actually adding that to the token. I don't want the double quotes as part of the token, just its contents. This is also, for now, a little naive, because there is no such thing as an escape character. It will just consume everything until you get to the next double quotes. Keywords are something we're not using today, but we will certainly use in the future. And for now, I'm just going to create a map of keywords, and I'm going to define a keyword as just being literally nothing at all. It's just to make the unordered map work. To all intents and purposes, a keyword is just a special type of symbol. And we might want to use keywords to change the behavior of this parser in real time. So we'll just double check that we're classifying the symbol correctly by searching for it in our map of keywords, and if it exists, then we'll classify that token as a keyword and deal with it appropriately later. Just before we test this, there is one more state with the string literals which can cause us a problem. If the user never puts in another double quotes, we'll keep consuming characters until we reach the end of the file or the input, in which point the while loop containing our state machine will exit. So if we're still in string literal state by the time the state machine has exited, then clearly we've not got the closing double quotes. So with that in place, let's take a look and see what our little machine can do. A plus B. Very good. Symbol operator symbol. I like that. A plus 1.234. Very good. Literal numeric. Let's do some binary. Plus some hex divided by a decimal. That seems fine too. We've also got these sort of additional symbols we've added in now. So we could have func 1, 2, 3, 4. There we are. So we've now got a symbol, open parenthesis, a numeric value, a separator object, separator object, separator object. That might be useful later on. Let's try x equals a plus b. Oh, we've got an unrecognized operator that time. What if we wanted to do print and then hello world? Well, here we've got a symbol called print, an open parenthesis, and a literal string, hello world. Let's just make sure that if we didn't have that in, what happens? Yes, there we go. Parenthesis not balanced. Well, parenthesis checker caught it out first, so that's even better. So let's just do hello without that, missing quotation mark. Good, good, good. I think the parser as we have it so far is robust enough to start being used for some actual solutions. But in order to be useful, we need to apply some sort of solver to it. And to do that, we need to have the Shunting Yard algorithm, which we did in the last episode. Fortunately, the way that we structured the Shunting Yard algorithm before is very easy to bring into the code at this point. So here is the code from the original video, and this was the main loop where we iterated through the characters of the expression, and we simultaneously classified the character and implemented the Shunting Yard algorithm. We ended up with a container of things in reverse Polish notation order, and we passed that container into the solver to then go ahead and work it all out. The Shunting Yard algorithm fundamentally relied on the sequence of characters in this expression. We don't have that anymore. We now have a sequence of tokens in a container, but otherwise it is exactly the same. So I do require a little bit of trust when I do this, because I'm not going to talk through every single line of code here. But if you've watched the first video, some of this should look very familiar. I'm going to pass in our vector of tokens into a newly created function called solve. And then I'm going to paste in the Shunting Yard algorithm as we had it from the previous video. Except this time, rather than being characters of a string, they are our tokens in our container of tokens. But other than that, it is functionally identical. You can see that it looks at what the type of the token is and then behaves accordingly. Was it a literal numeric? Was it parentheses? Or was it an operator? And if it was an operator, was it the unary operator or not? And apply the order of precedence rules. If it can't do any of those things, because we do have tokens now it might not understand, for now I'm going to throw this compile error that the solver contains elements that cannot be solved yet, ominously. After we've applied Shunting Yard, just as before, we need to drain that holding stack and then implement the solver. Now it makes an assumption that intrinsically we only have divide, multiply, add and subtract. There are a couple of subtle differences here, but it is almost identical to the code in video 1 again. So I'm not going to spend any more time on it than that. This means as part of our main test program loop, we can now call our solve function on the vector of tokens that's been passed back from our parse function. And if there are any problems, we'll catch the error. So let's take a look. 1 plus 2 times 4 take 3. That's our classic that we've been using all the time. Now we know we can mix that up a bit. I've got a feeling we trust that the Shunting Yard will get things in the right order, but let's try some of the different numerical techniques we've got now. So we've got 0b, 0, 1, 1, 0, which is 6, plus 0x, 1 in this case. 6 plus 1 is 7. So we've got two different numeric literal types, and it seems to be parsing those just fine. Minus 100.1 times 99.67. Well, it's handled the unary operator and multiple decimal points just fine. Let's give it something it doesn't quite know yet. F of 1, 2, 3. Expression contains elements that cannot be solved yet, so it doesn't know anything about symbols or separators. 0xff divided by 2.0. 127.5. We remain in the double domain. And to leave our application, quit. Oh. Well, I know there was a lot to get through, but I think it was necessary to cover some of these fundamentals to make sure that we have a robust solution moving forwards. So far, what we have developed is nothing more than a very simple calculator. It can only do 4 different operations. And it tends to do everything instantaneously. We can enter one string of input and press enter, and it will give us a solution. That's all well and good, but it's not really a computer program. There's nothing that implies sequence. There's nothing that fosters reuse. And we've not even looked at things such as input and output variables and memory. Well, all of that fun is to come in subsequent episodes. So if you've enjoyed what you've seen so far, give me a big thumbs up please, have a think about subscribing, come and have a chat on the Discord. You'll notice a link below to the code for this in the GitHub repo, and I'll see you next time. Take care.